Service equipment is a distinct category defined in the National Electrical Code as the equipment connecting supply conductors to a building's wiring system. This includes the disconnecting means and overcurrent protection for the building. Several types of service equipment exist. Firstly, service entrance panels, which are panel boards used as service equipment. Secondly, meter main combinations that combine a meter and a disconnecting means. And thirdly, all-in-one service enclosures. These enclosures integrate a meter socket, service disconnect, and branch circuit protection. It's important to understand the distinction between a panel board and what some refer to as a lighting and appliance branch circuit panel board. The National Electrical Code defines panel boards as equipment containing circuit breakers or fuses that distribute electrical energy to lighting, appliances, and other equipment. National Electrical Code Section 408.36 mandates that panel boards be protected by no more than 2 main circuit breakers or sets of fuses. This rule applies universally to all panel boards, regardless of their location or purpose. Let's analyze a couple of installation scenarios. In the first installation, the requirement to rewire GFCI receptacles to comply with National Electrical Code Section 408.36 was correct. However, the all-in-one service enclosure should not be classified as a lighting and appliance branch circuit panel board and thus doesn't need to adhere to those specific requirements. In the second installation, the interpretation that the all-in-one service enclosure is a lighting and appliance branch circuit panel board simply because it contains a single circuit feeding a lighting load is not accurate. The enclosure is service equipment and should not be treated as a typical panel board. The National Electrical Code does not prevent service equipment from supplying branch circuits, including circuits for lighting and appliances. It's crucial to recognize that an all-in-one service enclosure is a legitimate type of service equipment, and using it does not inherently violate the code. When evaluating installations, inspectors need to accurately distinguish between service equipment and panel boards. Misclassifying service equipment can lead to incorrect interpretations of the National Electrical Code and unnecessary rework. To ensure compliance, always refer to the definitions within the National Electrical Code and understand the intended function of the equipment. For example, a 100 amp all-in-one service enclosure with 6 spaces for branch circuits is designed to provide a compact solution for service entrance and branch circuit protection. The enclosure typically includes a meter socket and spaces for circuit breakers, eliminating the need for separate main disconnect in some applications, provided it meets the requirements for service disconnecting means as outlined in Article 230 of the National Electrical Code. When installing an all-in-one service enclosure, ensure that the number of disconnecting means does not exceed the maximum allowed by the code. Generally, up to 6 circuit breakers or sets of fuses can serve as the service disconnecting means. The overcurrent protection should be properly sized and coordinated to protect the service conductors and the downstream circuits. Also, the enclosure must be suitable for the environment in which it is installed, considering factors like weather exposure and potential physical damage. Branch circuits within the enclosure should be wired according to the National Electrical Code requirements, including proper conductor sizing, overcurrent protection, and grounding. Ground fault circuit interrupter protection should be provided where required by the code, such as for receptacles in damp or wet locations. In mobile home applications, the all-in-one service enclosure can supply power to the mobile home feeder. The feeder conductors must be sized according to Article 550 of the National Electrical Code, and the overcurrent protection should not exceed the ampacity of the feeder conductors. A grounding electrode system must be established at the mobile home, and the neutral and grounding conductors must be properly separated. When connecting a receptacle to the all-in-one service enclosure, use a receptacle that is listed and suitable for the intended use. The receptacle should be properly grounded, and ground fault circuit interrupter protection should be provided if required by the code. Remember that understanding the definitions and requirements in the National Electrical Code is crucial for ensuring safe and compliant electrical installations. Always consult the latest edition of the National Electrical Code and seek clarification from qualified professionals when needed. Let's delve into a more detailed explanation of key National Electrical Code sections relevant to service equipment and panel boards. Firstly, Article 100 defines essential terms such as service equipment, panel board, and overcurrent protection. Understanding these definitions is foundational for interpreting and applying the code correctly. Secondly, Article 230 covers service entrances, addressing the requirements for service conductors, disconnecting means, overcurrent protection, and grounding. This article provides guidance on how to properly connect the building's electrical system to the utility supply. Thirdly, Article 408 focuses on panel boards and switchboards, specifying the requirements for overcurrent protection, conductor sizing, and marking. This article helps ensure that panel boards are installed and maintained in a safe and reliable manner. In addition to these articles, it's important to be familiar with other relevant sections of the National Electrical Code, such as Article 250 on grounding and bonding, Article 310 on conductor ampacity, and Article 550 on mobile homes. By thoroughly understanding these code sections, you can minimize the risk of errors and ensure compliance with the National Electrical Code. Let's clarify some common misconceptions regarding service equipment. One common misconception is that all panel boards must have a main breaker. While many panel boards do have a main breaker, it is not always required, especially in service equipment where multiple disconnecting means are permitted. Another misconception is that service equipment cannot supply lighting and appliance circuits. As mentioned earlier, the National Electrical Code does not prohibit service equipment from supplying these types of circuits. However, it's essential to ensure that the overcurrent protection is properly sized and coordinated to protect the conductors and equipment. Another area of potential confusion is the application of ground fault circuit interrupter protection. Ground fault circuit interrupter protection is required in many locations such as bathrooms, kitchens, and outdoor areas. When installing ground fault circuit interrupter protection in service equipment, it's important to follow the National Electrical Code requirements for wiring and testing. Finally, always verify the listing and labeling of the equipment you are using. Listed equipment has been tested and certified by a recognized testing laboratory, providing assurance that it meets safety standards. When selecting service equipment, choose equipment that is suitable for the intended application and environment. In conclusion, understanding the differences between service equipment and panel boards is crucial for ensuring compliance with the National Electrical Code. By following the code requirements and seeking clarification when needed, you can create safe and reliable electrical installations. Always consult the latest edition of the National Electrical Code and consult with qualified professionals when necessary. Remember that electrical codes and regulations are constantly evolving, so staying up to date on the latest changes is essential for maintaining compliance. Consider attending continuing education courses and seminars to enhance your knowledge and skills in electrical safety and installation practices. Furthermore, it's important to develop a systematic approach to electrical inspections. Before starting any work, review the plans and specifications to ensure that the installation meets the code requirements. During the installation, regularly inspect the work to identify and correct any potential issues. After the installation, perform a final inspection to verify that all requirements have been met. Document your inspections and keep records of any corrections or modifications made. This documentation can be valuable in case of future questions or disputes. Moreover, foster open communication with electrical inspectors. Inspectors are valuable resources who can provide guidance and clarification on code requirements. Don't hesitate to ask questions and seek their input when you are unsure about something. Remember that the goal of electrical inspections is to ensure safety and compliance, not to penalize or punish. By working collaboratively with inspectors, you can help create a safer electrical environment for everyone. Also, consider joining professional organizations related to the electrical industry. These organizations provide opportunities for networking, education, and advocacy. By participating in these organizations, you can stay informed about the latest industry trends and best practices. These groups provide valuable resources for professional development and can help you connect with other professionals in the field. Let's discuss the importance of proper conductor sizing and overcurrent protection. Conductor sizing is critical for ensuring that conductors can safely carry the intended current without overheating. Overcurrent protection devices, such as circuit breakers and fuses, protect conductors and equipment from overloads and short circuits. The National Electrical Code provides detailed tables and calculations for determining the appropriate conductor size and overcurrent protection for various applications. When sizing conductors, consider factors such as the ampacity of the conductor, the ambient temperature, and the number of conductors in a raceway or cable. Overcurrent protection devices should be selected based on the ampacity of the conductors and the requirements of the equipment being protected. Improper conductor sizing or overcurrent protection can lead to overheating, fires, and equipment damage. It is also beneficial to use appropriate wiring methods for the specific application. The National Electrical Code specifies different wiring methods for various locations and environments. For example, in wet locations, conductors must be installed in waterproof raceways or cables. In hazardous locations, conductors must be installed in explosion-proof raceways or fittings. Choosing the right wiring method is crucial for ensuring the safety and reliability of the electrical system. Another important aspect of electrical safety is proper grounding and bonding. Grounding provides a path for fault current to flow back to the source, allowing the overcurrent protection device to trip and de-energize the circuit. Bonding connects non-current carrying metal parts to create a low impedance path for fault current. Proper grounding and bonding are essential for minimizing the risk of electric shock and preventing equipment damage. The National Electrical Code provides detailed requirements for grounding and bonding, including the size and type of grounding conductors, the location of grounding electrodes, and the methods of bonding metal parts. When installing grounding and bonding systems, it's crucial to follow these requirements carefully. Additionally, consider the impact of harmonics on electrical systems. Harmonics are distorted waveforms that can cause overheating, equipment malfunction, and reduce power quality. Nonlinear loads, such as electronic devices and variable frequency drives, can generate harmonics. To mitigate the effects of harmonics, consider using harmonic filters, reactors, or other mitigation techniques. It's also important to perform regular power quality monitoring to identify and address harmonic problems. When designing electrical systems, consider the potential for future expansion. Providing spare capacity in panel boards, raceways, and conductors can make it easier to add new circuits and equipment in the future. It's also important to plan for future technology upgrades, such as the installation of electric vehicle charging stations or solar power systems. By planning for the future, you can avoid costly and disruptive modifications later on. Furthermore, consider energy efficiency when designing electrical systems. Using energy-efficient lighting, appliances, and equipment can reduce energy consumption and lower utility bills. The National Electrical Code provides requirements for energy efficiency, such as the use of occupancy sensors and automatic lighting controls. It's also beneficial to conduct energy audits to identify opportunities for energy savings.